there folks, Mr. G here with another educational video. Today we're going to be starting the last topic in chemistry, and that is called Kinetic Molecular Theory, or KMT for short. So that's this thing up here. Often we say KMT for short. And we'll talk a little bit about what this is, but first make sure you write your name at the top of the notes here, and a reminder, you can always find these notes in our classroom, so just over on the side there. I've got printed versions of everything, including the worksheets, any of the other questions that you have to do, so please make sure you come, especially if you don't have your own printer. We are day 2, period 1. Today is December 9th, and this is going to be page number 7 of our notes on chemistry. So, kinetic molecular theory and states of matter. We're going to actually start with talking about the different states of matter. Now, most people are familiar with the 3 common ones: solid, liquid, and gas. So solids, those are solid shapes. They hold their own shape. So for example, this stapler right here, very much a solid. It holds its own shape, and it has a constant volume, and I can't really compress it. If I try and press on the sides of this stapler, I can't squeeze it into a smaller volume. And that's what we mean by compression here. It's something that's squeezed together, so the same amount of mass in a smaller volume. So we don't mean about stretching or squishing something, because what we're doing there is we're changing the shape, right? But we're not making it a smaller volume, right? All we're doing is changing the shape that the volume is in. But it would have a constant volume, and usually it holds its own shape unless, it's malleable, maybe you can bend it a little bit. But a liquid is different, right? A liquid would be like the water in my water bottle here. So that liquid always takes the shape of the container. So the water in my water bottle fills up kind of the bottom part, however much is left. I don't think there's very much left in my water bottle here. So it takes the shape of whatever it's in. If I were to take that water and pour it into another glass, that water would take the shape of the new glass. But it has a constant volume. So the volume in my water bottle poured into another cup would still have the same volume, just a different shape. And again, we can't really compress it, so you can't squish water down and make it have the same amount of mass, but a smaller volume. Gases, on the other hand, take the shape of the container, just like liquids. So if we think about gases, we can think about the air in this room. So they would take the shape of the room itself, and it also takes up the volume. So gases always fill up the entire volume here. If you've ever released like a fog machine or something like that, you'll see that the smoke or the fog spreads out in the entire room. It takes out the entire volume. It doesn't just take the shape. But gases can be easily compressed. And in fact, you can test this if you've ever gotten like a balloon. So if you have like a balloon and you blow it up, there's some gas trapped in there, you can actually squish it down if you're careful. You can make it have a smaller volume. If you squish it too much, it's going to pop, but you can compress that air. Now the fourth one is a little less common. You might not be familiar with it. It's called a plasma. And in a lot of ways, it's the same as a gas. Takes the shape of the container, takes the volume, and is easily compressed, but the main difference is that it's made of charged particles called ions. One of the common examples of this is lightning. Lightning is an example of a plasma. It's made up of charged particles. In particular, it's the air particles that when the electricity passes through, they split and they become charged particles. When a liquid changes shape and it's poured into a wide, shallow container versus a skinny container, does the volume change? No, the shape changes because it's in a different container, but the amount of space it takes up is the same. So the water in my water bottle, if I pour it into another glass, the volume doesn't change, the amount of water doesn't change. All that changes is the shape of the container holding it. And since it's a liquid, it takes that shape. It forms into the new shape. How is taking the shape different from taking the volume? Well, when we take the volume, it means that it expands or compresses to fill the entire space. So it doesn't just take the shape, it fills up all of the space available. Whereas if it just takes the shape of a container, it would fill up as much as it can, right? So for my water bottle, maybe it only fills it up to here, but it takes the shape of this sort of rounded surface of my water bottle. How is a plasma different than a gas? The main thing here is that a plasma is charged particles, a gas is just neutral particles, no charge. So I said lightning. Another example of plasma is the sun. So the sun is a giant ball of plasma, as well as our fluorescent lamps. So that's the lights just at the top of the room right here. Those lamps, inside of them, there's actually a plasma, and that plasma is what's emitting the light, so we can see. So now that we're familiar with all of the different states, now we can talk a little bit about about what kinetic molecular theory says. So let's break this down. Kinetic, that refers to kinetic energy, which is the energy of motion. So first off, this is talking about things that are moving. And in particular, we're looking at molecules, or really little things that are moving. So molecules, atoms, particles. This is talking about the movement of really little things. So, does the book sitting on your table have kinetic energy? It does, actually. Even though you'd think, oh, it's sitting on the table, it's not moving, the particles inside the book are moving. So they're actually in there and they're shaking, they're vibrating just a little bit. Kinetic molecular theory explains this. Kinetic molecular theory says that all matter is made up of very small particles, so atoms, molecules. These particles exist in empty space, and they stay together because they're attracted to each other. So we have this empty space here, and these particles, they stick together because there's some sort of attraction, so a force pulling them towards each other. They're constantly moving, and the energy that they have makes the particles move. So they're kinetic energy. That's why they move. So if we add energy to particles, how does their movement change? Well, they would move faster, right? If we think about energy of motion, something moving faster has more energy, and they tend to move farther apart. So as they have more energy, they're moving faster, they're more likely to get farther away from each other. And this force pulling them towards each other doesn't do as much. It's not able to hold them together if they're moving much faster. So our kinetic molecular theory explains the three different states in terms of how particles are moving. In our solid, the distance is very close together. So they're very close, and there's a strong attraction between all of our particles. So they're really tightly clustered, and there's a really strong interaction. And they move, but they only vibrate. They don't really move around, so they just kind of jiggle around in place. A liquid, on the other hand, is also close together, though not as close as a solid. They are still pretty close. And there is some attraction, so there's some force holding them together, but these particles are allowed to slip and slide past each other. So you could almost imagine like balls in a ball pit, right? They can kind of slide past one another. And there is some attraction. They are close together, not as close as a solid. They can sort of slip and slide and move. Gases, on the other hand, are moving in all sorts of different directions. And the particles tend to be very far apart. There's almost no attraction between them. They're kind of just bouncing off in random directions. And the movement, they tend to move quickly and in straight lines. So they just move around, and once they hit the edge of the container, if you remember, gases, they fill up the volume of the container. So they travel in straight lines in all sorts of different directions until they bounce into a wall, or maybe they bounce into one another, but they are just kind of flying around. And so these three states, the way they move, explain the way the particles are moving inside of them. So this is how kinetic molecular theory explains these different states. For plasma, it's very much like a gas, except for instead of being neutral particles, they're charged particles. And kinetic molecular theory can actually explain a lot of things. And we'll talk about this in the follow-up episodes. For instance, water has surface tension. So if you've ever tried or seen maybe some bugs or other things balancing on top of water, that's because the molecules of water in this liquid, they're not solid, so you can't stand on it in the same way you'd stand on the ground. But if you don't put too much weight or too much force on the surface, the liquid can actually hold itself together. Those particles are attracted to one another and they can actually hold that surface. So that's where something like surface tension comes from. That's the end of our video here. Make sure that you check Teams for all of the assigned questions, for any other readings, or any other videos that you have to do, and I will see you all in the next video.